So, good morning, everybody. I am going to speak an hour about network management, managing or being managed. It's going to be a tour through some of the management protocols we've had in Erlang over the years. But before I do that, let me start by introducing myself. Some of you know me very well, but I think a majority of the audience here may have heard of me, but don't know who I am. So I worked in the early days at the CS lab when we were developing Erlang in the good old days. And so during the 19s, all of the 1990s actually, I was working with a virtual machine and did a lot of work on the virtual machine, and large parts of it remains there. So things I did at the time were things like ets and dets and amnesia and the garbage collector, binaries, the driver architecture, the bit syntax, lots of stuff. Distribution, lots of stuff. A lot of that work together with Tony Rogvall. So this was during a period where the emulator grew from, I think, 8,000 lines of C code when Tony and I started on it, and it's been growing since, and now it's a beast. It's a fantastic beast. It's an amazing piece of engineering, and it's, well, whatever. And since then, I've been, so Joe showed a picture the other day, and referring to the DNA of Erlang, and he was showing Bluetail, Klarna, and Tailf, and I can relate to that because I was a founder of all those three companies. And currently I'm working Tailf, which is a company specializing on network management. We started in 2006, and so I've acquired a few opinions on network management during these years. And I'd like to share some of them with you today. And I'll be doing it in the form of going through management protocols that we've done in Erlang over the years. So I'll be showing some software which is part of OTP and some which is not. And a lot of this software, a lot of you have used over the years. So let's start with what's the story, what's the task. A lot of you are writing software that needs to sit somewhere in some actual commercial environment or at some wherever your software is supposed to sit. If it's real software that's supposed to be used by others than engineers, then the software needs to be managed. And there are two components in managing software. It's having software in your software which allows it to be managed. And then, so that's the agent. This is SNMP speak. I don't actually know where the name agent comes from. You could say server. And the other end is the client, which in SNMP speak is manager. So that's the client that connects to somebody and manages it. So at Tailf, we do commercial software to do precisely this. We're doing the agent side, which we sell to companies that do switches and routers and whatnot. So if you go buy a Cisco router today, you'll find our software in it. And vice versa, if you have 1,000 Cisco switches and 1,000 Juniper routers and you need to manage them, we do that sort of software as well. So that's what we do. And we export that software. And it's commercial software and it's not open source. In the beginning was the config file. This is the easiest way to configure a program. This is something all of you have done. And there are actually good and bad config files as well. This is an example from ejabberd.conf. It's just an Erlang term. Do you like it? It's horrible. It's horrible. There's no way for the user to look at an existing config file and figure out there's no schema, there's no nothing, there's no guidance for whoever is supposed to edit this file. And I bet you, if you do an error configuring the ejabberd, the message you get back is not going to be super instructive. So the only thing that's good about this is that it's really easy for the programmer doing the config file. It's a one-liner in Erlang to read in the config file. Not good. Don't like at all. Slightly better, but still not good. So this is from jaws.conf. Jaws is another of my project which I started many, many years ago. And this is not my finest moment. It's ages ago, and it looks as if it's some kind of XML-ish thing. I'd probably seen XML, but didn't grasp it at the time. Horrible, horrible. And if you look at open source projects, there are some that have really, really nice configuration file syntaxes. So my favorites is the config file for Nginx. So if you're going to do a config file format, have a look at the Nginx config format. That's a recommendation. An alternative is old Microsoft-style INI files. They're actually okay. This is not. Okay, so now I'm going to go through a number of pieces of software that we have in OTP that has been, so this is, the reason I'm starting with the ASN.1 compiler is the first piece of management software that was written in Erlang. That was, maybe it's not, but it's one of the first pieces. So ASN.1, it's an IDL. It's a strange IDL. It's been around for ages. It originates from CCITT, and it was heavily used in OSI networking stacks. You define data structures like the one on the right there: people, blah blah blah, person, location. And then the ASN.1 contains marshalling and coding rules. So you have one of these data structures, you can get it into a stream of bytes, send it on a network, or write it on a file, and vice versa. You can reproduce the original data structure at the receiving end. Not rocket science. It was heavily used in the disgusting OSI management protocols, CMIP at the time. So this was early 90s. When we did this. And Ericsson, for example, was completely infested with the idea of that the OSI protocols, and that was not just for management. You remember Solaris came out with a version that supported the TCP using that horrible, what was it called, TLS? No? No one remembers? Come again? Anyway, horrible stuff, and it's all gone, and no one is missing it. So I did the first ASN.1 compiler, and Kenneth completely rewrote it and making it actually workable, usable. This is a little bit. This is a nice slide actually. It's a long jump in time. So the original code was written in the early 90s, but if we look at the implementation now, it looks beautiful. Look at this code. It's fantastic. It's bit syntax at its best. Some data comes in, and just right at the header, you pick it apart, and so this is almost a specification of the protocol itself. It's fantastic. I guess this is Kenneth's code. It's good that we have it. It's still, the language is still heavily used within a number of IETF RFCs. So all of the security-related RFCs, so all of those, the security framework surrounding ISAC-MP for IPsec, and all of those RFCs, they're using ASN.1, and I think they're using it in DNSSEC as well. So it's still relevant, highly relevant. So it's really nice that we have it, and I'm sure that the existence of it has facilitated a number of different protocol implementations in the Erlang community over the years. So it's great that we have it. The alternative would be horrible. Here's another one. Disgusting little protocol. I said that before. Early 90s, telecom industry was all confused about OSI. And I was working at the CS Lab, and Joe and I, we'd had a little session out to a place in Kungens Kurva where they were doing cross-connect, digital cross-connects. And they were all about OSI management, and it was so much vaporware, and there was no actual code, and they were all talking about the OSI specs and CMIP, and it was. And then at the time I heard of SNMP, which just had come out then at the time, and I thought there's got to be an easier way than the OSI stuff. So I signed up Martin Björklund and Claes Wikström as thesis students at CSLab. Then this must have been maybe 1992 or something like that. And so they did a proper SNMP implementation, and that's pretty much the same one we still have in the OTP distribution. So, referring to the actual protocol itself, one thing they did get right, which very, very few management, I'll be mentioning in quite a number of different management protocols here, and a lot of them did not get this one thing right. So SNMP, it's more than a protocol. It also defines the payload using a formal data description language, SMI. So you have the protocol to send to from the manager to the agent, do this, what's the counter, what's the value of that, blah, 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 blah. So that's over the protocol. But the actual payload, whatever comes back in the response from the agent when you read a counter or whatever you do, a traversal table, that data is defined formally in the SMI language. So this is one of the things they actually got right. This is what makes it possible for management software or engineers doing the manager side to have a look at those SMI files and see, so what kind of data do we have on that device? The alternative is ad hoc, random. If you get a REST API, for example, it's ad hoc, curling to the device and see what you get. Yeah, and figure out from the names of things you get what it actually means. So this is one of the things they actually did get really, really right. SNMP is ubiquitous. It's all over the industry. So whatever you build, if you're going to install your software in another alien environment, like at an operator or at a bank or in a data center or wherever, you're bound to have an SNMP agent on your software. So it's really good that we have this high-quality SNMP agent in the OTP libraries. So don't be afraid of adding it to your application. It's a breeze to write your own tiny little MIB, define your counters, feed that into the SNMP compiler, and then you have an SNMP agent on your software, making it easy for the environment where your software should go, making it easy for them to monitor your software. And mind you, I say monitor, because you can actually do two things with SNMP. You can read data, but you can also write data. If you look at a Cisco router, for example, they got a slew of MIBs, but they read only, all of them. All these MIBs in the RFCs, they defined some read-only data and some read-write data. But Cisco turned it all read-only. And there's a good reason for that. They don't want some SNMP manager to send spurious SNMP PDUs to their routers reconfiguring BGP. That's way too dangerous. And so in the networking industry for the past 20 years, there are fairly few examples of successful SNMP read-write projects. I know that some telcos, Ericsson is one, Alcalu is another. I think Alcalu was more successful with this than Ericsson. They had a manager called SAM, which was SNMP based, and that's actually still in production today and considered a good manager. So, but in the rest of the networking industry, which is more IP oriented, is read-only. And I do not recommend to use SNMP for read-write. The last bullet here is bugger. It's one of the things they really got wrong with SNMP. So say that you're running a switch or a router or your piece of software, whatever. There's no way to, over the SNMP protocol, acquire the configuration, the actual config of the device, and then feeding that into another. There's no way to get a copy of the config. You cannot take a backup of the config over the SNMP protocol. So that pretty much limits the usefulness of the protocol. Nevertheless, it's good. And as I said before, it's fantastic that we have it. If we didn't have it, the alternatives would be horrible. I mean, you would have to interface to NetSNMP, or it'd be really ugly. The existing implementation exists there. It's an OTP application, as most of you already knew. Authors, Martin Björklund, Claes Wikström, and Peter Högfeldt, who used to be an active member of the Erlang community, participated as well. 56,000 lines of code. And this is the compiler, the client, or the manager, I should say, and the agent, the server. Here's some code. This is, so the previous code you saw was the bit syntax. That's classical protocol implementation code for Erlang. This is the other typical classical protocol style of decoding. This code gets a sequence of bytes. First byte is 164. It's a trap. Then you have a function that takes the remainder and does something. And then a bunch of functions that picks out something and returns the remainder. Picks out something, returns the remainder from a sequences of bytes. It's classical code. It's a matter of taste if you prefer to use the bit syntax or have the parser go through a sequence of bytes. And I bet you this code is old, and if it was to be rewritten in today, I'm sure they would have chosen the bit syntax. Here's another one. Very unnice. Mr. Korba is actually in the room. Steve Inoski, I think he was one of the part of the original team that developed the first Korba spec. There is a Korba, good Korba implementation in Erlang, done by Lars Torssén, Per Danielsson, Peter Lundell, and Niklas Eklund. Niklas is working at TLF just right now. So the reason we have it is because it's mandatory to have it for configuration interfaces in the GSM network. So a base station must, according to the specs, I don't know if all base stations do, but they must have a Korba server so that you can manage the base station over the Korba protocol. It's nothing more than a glorified RPC mechanism. It's a big beast, but if you look behind the lid, there is not a lot more there than the nicely, easily understandable Sun RPC. It's 29,000 lines of code. That contains the IDL compiler and everything. Typical bit syntax code, beautiful code to decode the packet header here. I love this type of code. Now we're getting something which is slightly more modern. What I've said so far are ancient style of protocols that most of you young guys here find arcane probably. But even if SNMP is arcane, you're still going to have to deal with it. Whereas Korba you can probably ignore. This you cannot ignore though. REST, HTTP, HTTPS. So if you're building something, it's almost required today to have a web UI, and it's to have a REST API is becoming very modern. So main benefit of the REST, let me spend 30 seconds on what a REST API is. It's carried over HTTP. You can get a URL in the device or the application. You're getting back a set of resources which contain data and other URLs, and then you can get those as well. And then you can post and patch on those resources and those URLs, thereby over this REST API using curl. Curl is the typical, or a Perl program, or a Python, or an Erlang program for that matter. In this type of environments, these operator environments, where then guys running ops in this type of environments, they're typically Python and Perl shops, and they love REST APIs, all those guys. So main benefit of it is really easy to understand it, and it's super easy to get started. You power up this shining new box and it announces something over port 80 or 443, you can curl there and see, I'm getting stuff back here. And it's a structure. I can look. It's a JSON structure or an XML structure, and I can look at it. I can, from the names of the tags, I can guess what they mean, and I can continue to curl through there down the device. So it's really, really easy, and it's nice if you're an ops guy and all you want to do is patch up a little Python script to do some simple provisioning on this device or on this application. It's perfect. It's perfect. As I write here, if well designed, it's almost self-explanatory. And we have a slew of nice web servers and web technologies in the Erlang community now. So whipping up a REST API for your application or your device is a walk in the park. The negative, and this is a biggie. So REST is fine, but it's actually barely usable except for the case with the ops guy whipping up a Perl Python script to do some naive, simple provisioning. For integration into a larger context, it's useless, worthless. And that's because the payload is structured, but there's typically no formal definition of the payload. And that makes it virtually impossible for someone above to integrate towards your device. By guessing the tag names, they need to write custom code in order to integrate towards your device, which makes it horrible. And a lot of device manufacturers today, they proudly announce we have a REST API and we ship JSON structures, but that doesn't help. We can use XML Schema to define the payload, but that's pretty awkward. And as far as I know, there are no good formal ways of defining JSON structures. Maybe there are. I said before, there's a slew of nice web technologies to choose from. Personally, I'd go for yours, but that's because I'm highly biased. The other ones are fantastic. Yours has 35,000 lines of code. That last bullet here is not to be neglected. Maybe you should scrap all this web server and roll your own. It's a walk in the park to write a 50-line web server in Erlang. And the reason for that is because we have the packet HTTP option to TCP sessions. So if you create a socket like this is not news to, I guess, the majority here. But this is great stuff. You create this socket like that, and you're getting, and when you read, you're getting HTTP stuff, header, blah, blah, blah. You're getting the HTTP things on the socket. So it's, which is, what do you think, the shortest HTTP server done? Is it 50 lines? 10 lines, right. So this is not to be neglected anyway. We have fantastic SSL implementation, and these days it's an Erlang-based SSL implementation done by OTP team. Great work. REST continued. We have in REST, the payload is, it can be text, arbitrary text that you, whatever text you like. It can be anything. The most common is to have JSON structures or XML structures in the payload for your REST calls. We have fantastic support for both JSON and XML in Erlang. If I should do a recommendation, I'd go for the JSON payload. It's also hipper. XML, though, how much we dislike it, we are going to have to live with it. It's here to stay, and it's not going away. And there's no way that you can survive as a software engineer without being XML knowledgeable. You have to know what a namespace is. If you don't, you might as well go look for another job. We got several nice XML parsers to choose from, both DOM-based and SAX-based. The DOM-based parser, they read the whole chunk and represent that as one big fat tree that your code then later can walk and traverse. So the downside there is that you need to parse the whole thing before you can do anything. The SAX-based ones, they work on a stream, eating tokens, and then your code needs to act on those tokens and building tiny little stacks and doing things like that. Depending on the application, you need to choose one of them. So one of my favorite XML parsers is not Xml, that Ulf Wieger and several others here in the room here wrote many years ago. It's called Erlang, and the author is actually here, Willem de Jong, a Dutch guy. And it's really fast and it's really lightweight and it's easy to understand. It's at Tailf, we did our own, for reasons I'm not sure of actually, but that's what we did. Jokke Grebener did that. XML Schema, I absolutely hate it. It's the most horrible piece of engineering. It's meant, can you understand? It's meant to be read and written by humans. That's it's the schema. It's an engineer needs to. It's not meant for machines to generate it. You're supposed to write it with simple, complex types and all of that. It's horribly complicated. Nevertheless, you need to know it. That we have XML support. I bet you 9 out of 10, or maybe 4 or 5 out of 10, a lot of Erlang projects are using XML in some form today. Okay. Not to be underestimated. So we have an Erlang program, and we want to manage that, and we write the client in Erlang as well. Great stuff, right? Erl call. Using distributed Erlang, we can from the command line invoke any function inside an Erlang node. And eJabberD is controlled this way. It has some serious security implications. The whole management of the node hinges on the Erlang cookie file. Well, that's what you get, right? And the cookie file isn't as bad as you can think, because beneath it, we actually do have the Erlang security, the security foundations of the Unix file systems, and they're solid. So as long as you know what you're doing, basing your whole security of the management for the server based on file securities or maybe group security, fine. But you need to know what you're doing, and you need to be aware of it. So the Erl call, it's using term to binary and binary to term. It was mentioned yesterday. It's fantastic term to binary. And not only is it so easy, it's so easy to use, so that we're actually forgetting that we have this tree or queue or whatever data structure we have. We do term to binary on it, and so it's so easy to use. You actually tend to forget that what we're bypassing here is the entire IDL of Corba or SunRPC or ASN.1 or whatever other cruft they made up. We did away with all of that. Fantastic. There's a downside to it, though. There's always a pro, and there is always a con. The con here is that there is no formal document describing this structure. So, well, you win some, you lose some. Another really good thing about the turn to binary is that it is so fast. I don't know if you're aware of how fast it is compared to traditional marshallers, the marshallers you find in Corba, for example. So it's super fast. And it also produces very compact output. So it's great technology. Number 3 here, normal socket to localhost and sending term to binary. Yours is controlled this way. So instead of using Erl call, just create a socket and send terms on it. And again, make up some other file-based security mechanism, so that only if you are within this group or within this, if you are this user or something like that, you need to be able to figure out the cookie, send it on the socket, and this is how yours is doing. It's remote controlling. You have the server, you want to control the server. At least you want to be able to stop it, right? That's number 1, without using kill. So I mentioned this. There's a positive and a negative to the IDE. The interface is embedded implicitly in the client-server code. This is not good, right? So in order to figure out what can go on the wire here, what are the messages, we need to go into the code and actually look at the code and see what it decodes and what it does on the structure it decodes. Maybe the code isn't even comprehensive. It's not covering all the cases. We don't know, and we'll never be able to find out. So that's the downside. So you need to, as they said in Denmark, ta det onde med det gode. There are great C and Java implementations of the external term format, so it's really easy to interface to the external world. I don't know if there are Python implementations. I suppose there are. 3 here, showing term to binary here, term to binary. So we have a term, a tuple. We can produce a binary. You all know this. Great stuff. This is, by the way, this is also the basis for distributed Erlang. Distributed Erlang is obviously using this to send the data over the wire with an additional really clever trick, and that is a tiny little atom cache. So atoms in the term to binary format, we see Kalle here. So Kalle goes verbatim. So 104 means atom. No, 100 means atom. No. 100 means atom, and 05 length of atom, and then counts 107. Counts the actual atom. So atoms go atoms go verbatim on the wire, whereas in distributed Erlang we're using a little clever trick whereby atoms go into a little atom cache table, and the first time the whole atom goes, and the second time just an index into that 256 byte cache goes over the wire. So how am I doing on time? Come again? Okay. So I'm going to spend some time. So I said I'm working at a company called Taileft right now, and we are in the network management business, and so obviously we're writing network management software, and I need to mention some of the software that we have, and because that's the topic, right? So NETCONF is a new protocol defined a couple of years ago by the IETF, and well, not new. It was invented by Juniper, and it has an accompanying RFC called Yang. And so those two protocols, NETCONF and Yang, they are the equivalents of the SNMP protocol RFCs and the SMI RFCs defining the RFC defining the SMI language. So as NETCONF defines the protocol, and Yang is a modeling language to define the payload for that protocol. So this is the first time the networking industry got it entirely right vis-a-vis management aspects. And by right, I mean that a device or an application is shipped to a customer, and then that customer is tasked with the task of integrating that piece of equipment into their management, whatever management applications frameworks they have. So in order to do that, the device must have a crystal clear interface. Not just the protocol, how you talk to it, but also what data can you send to it and what data are you getting back. How you talk to it is precisely defined by the NETCONF protocol, which is a well thought through XML-based RPC mechanism. It's nice. I'll show you some examples of it soon. Yang, though, is used to define the XML payload in the NETCONF protocol. So you're using Yang to define the data structure. Here's an interface, it's got these leaves, and so it's an alternative to XML schema. You define, it's a readable and writable version of XML schema, and it's designed with readability in mind. So RFCs are written once, but they're read many times over and over again, and that means that it must be easy for the end user to read the spec, or the RFC. Another thing they got really right here in this protocol is they're making they're distinguishing between what is config data and what is not. And so when you're writing your Yang specifications for a device, you need to define, this is config, this is not. It sounds easier than done. Sometimes the line is blurry, but a lot of the time it's not. And the way to think about it is that if I would like to take a backup, write it on a file, and then next week reinstall from that what is config. That's a good way of thinking about it. Everything is text-based here as well, so you can get anything into your Emacs buffers and manipulate it. Lovely. This is not the case with a lot of the other management protocols. Transactions. So this is something I'm going to spend some time on here now. When we reconfigure things in a number of applications, or we reconfigure a network, we want to be able to do that as a transaction. So say I want to change 2 routers and 1 switch. I send that to change to router 1 and router 2 and then to the switch. And the switch says, no, I don't like this. It says blah. Maybe you're talking CLI to it and it comes back with an error string. At this point, you're pretty much screwed. There's no easy way to figure out. If you're talking CLI to the device and you've provisioned a number of VLANs, created virtual interfaces, or maybe created a number of VRFs on a router, there's no easy way to figure out how to undo that. There's no reverse. Same thing if you sent a bunch of SNMP PDUs, or if you issued a bunch of curl requests to your application, and somehow the manager, well, no, I'm changing my mind. I don't want this. There's no easy way. There's no way at all, actually, to automatically undo what you just did. So what they did here in the NETCONF protocol, they got it right by getting that into the protocol. The mechanism that NETCONF is using is called confirmed commit. And it's like two-phase commit for databases, sort of, but it's much cooler, and it's networky. So these are messages that would go from the manager to the agent. We're locking the candidate, and we do that for a number of devices, the 2 routers and the switch. We're locking the candidate. No one else can touch this guy now. Then we're sending an edit config RPC. And this contains the actual payload. This is what comes here. I want to create a VLAN here, blah, blah, blah. This is the payload. I send that to the candidate of the 3 devices. You got it, you got it, you got it. They're all happy with it. They reply all OK. So far, we've only modified like the shadow copy of the config on the device. Next thing we do, we send a commit with a confirm tag there. At this point, all these guys, they will go live with this proposed change. So after they all get the commit confirmed message there, the top one there, they're all alive. And this thing is now operational on the 3 devices or on the 3,000 devices. If they do not get the commit message within a stipulated timeout, they will automatically roll back. If they lose the SSH socket to the manager, they will automatically roll back. So this is a way to push out a change in the network, view your SNMP trap logs and see if all shit is breaking, hitting the fan. No, it looks good. You see the commit message. So it's a way of staging the thing towards the network. It's not like two-phase commit towards databases, because you typically need human intervention there at precisely between these 2 messages. So this is great stuff. Juniper invented it, and it's part of the NETCONF protocol. And this is the technology that makes it possible to do network-wide transactions. You want to push out a change to a bunch of devices, and all of them get it, or none of them get it. Not an easy task. And if the devices speak, all they have is a homegrown, fancy, JSON-based REST API, there's no way to do this. This is some Yang code. List, blah, 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 blah. It pretty much has the same semantics as XML schema, sort of. It's used to define payload, and the payload is an XML. It's readable, and it's almost self-explanatory. We have, this is not particularly interesting. So this is a tiny little way of getting the data out from a device. You can send a get config request to it, and you're getting the payload back in an XML format. The CLI is ubiquitous. The network industry is, every device has a CLI. You cannot buy a device without the CLI. There are two main CLIs in the network industry, where one is completely dominating, and it's a Cisco CLI. So we have, at TLF, we have an implementation of a Cisco CLI. You define your data models in Yang, and you get a Cisco CLI for it. And basically all NEPs, network equipment providers that are doing switches and routers, they're anal about it's got to be a Cisco CLI, and it's got to look exactly like this. So the CLI has two aspects. One is entering config. So this is config, show running config, blah, blah, blah. You can do no and set and things like that. The other aspect of the Cisco CLI is the show commands. You do show routes or show BGP or show ports, and you're getting stats back. That stats is unstructured text. And this is how the networking industry is built. So we have these huge networks today, right? With billions of dollars worth of switches and routers. And all those switches and routers, within all the Facebook racks and whatnot, they all have that CLI. So in order to provision things on these devices, we have Perl scripts that screen scrapes towards these switches and routers. And that may work well for config, fine, that's fairly structured anyway. But what's worse is that those same Perl scripts, they're used to do show routes and show BGP in order to, and they parse the text output. And this is how the entire internet is built today. So it's built towards a Cisco CLI, and it's built with Perl and duct tape. And that is a scary thought. And so there's a lot of work to be done in order to remedy that situation. And besides, this is an industry that is not like agile and ready to change. We think of ourselves, we can change, we're using new methods, we're changing languages, blah, 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 blah. These guys, they're conservative. This is another CLI. Juniper devices, the Cisco CLI, it's based on commands. You do setting commands. Whereas the Juniper CLI is a much nicer model. The idea is that you have a conceptual idea of the configuration as a tree, and the Juniper CLI manipulates that tree. That's easier, and it's a nicer idea. But the Juniper CLI is not at all as common as the Cisco CLI, for obvious reasons. This is the latest fad, SDN, software-defined networking. Openflow is getting all the rage now. Personally, I think it's not going to fly very high. It may solve some issues, some problems, but it's not something that Cisco needs to worry about. I don't think so anyway. So we have the view at TLF, we have the view that what you want is, say you have this network, millions of devices, different vendors, different brands, and firewalls, VLAN accelerators, switches, routers, whatnot. And you have this, and what you want as a network management programmer, you want to have a conceptual tree, which is the network. And what the network programmer then does is write programs that manipulates this tree. And so if we can get there, and we are there with TLF software, the programmer manipulates this tree and then commits over the tree, and whatever needs to be done is done. And it's so much easier, and that's a computer science task to manipulate the tree. We can hire a guy off university that knows how to manipulate the tree. Whereas the other task, or actually reconfiguring routers in the network, it's much more difficult. All the routers are autonomous because all these BGP and all those protocols, they're designed in order to, so each device should be able to function in its own right and only get its information from its neighbors. So we'll see where all this goes. The networking industry in Silicon Valley now is in turmoil, and everybody is arguing with everybody what should be done. And we'll see where it all leads. Regardless, the idea of programming the network instead of sending out those guys with black t-shirts, ponytails, and bad attitudes to reconfigure the router, that's a great idea. Yeah, we want to go there. And if you talk to management, they really want to go there. So Openflow is about separating the forwarding plane from the control plane. Forwarding plane is whoever ships the IP packets. Control plane, well, that's the CLI, sort of. And they should not be on the same device. That's the Openflow idea. So Tobbe spoke about our Openflow management solution. So we've done an Openflow controller in TLF as well that we've integrated into NCS, which is that tree I was talking about. And so now we can have nodes in the tree which are Openflow controllers. We're using TravelPing, flower from TravelPing, which is a sort of Openflow library routines, you could call it, to encode and decode the packets. Great software, great software. The last one is, this is where the networking industry wants to go. This is, we don't want to control switches and routers. We want to program services. So if you consider a VPN, for example, it's got its legs, and it touches a number of routers, and maybe you need to add a leg, maybe you need to make it multi-mesh, blah, 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 whatever. So as a programmer, you just want to talk about the VPN. You don't want to know all the, you don't want to go in, log into all the routers to do it. And error prone. And it's also the case that 10, 15 years ago, networks were more static. It was realistic to have the guy with the ponytail go and actually configure the router, and then you're done with it. Now networks are changing all the time due to different characteristics, due to different reasons. A virtual machine is fired up and it needs a new VLAN, whatnot. There's a lot of things that make networks change more often, and it's costly to do it. So this is where we want to go. We want to program services, and instead of controlling switches and routers. So that concludes my talk. So thanks a lot for listening.
Any questions? Yeah.
You said it's impossible to get all the configs via SNMP.
Yes.
But you can always get a string back. So if you have some kind of config well, you can have all the config in a string. So what's the problem with sending the whole string via SNMP, the number of numbers?
The whole configuration as a string?
Yes.
So you're proposing to have a field in the MIB where one of the fields is a string containing the entire config?
Yeah.
Okay, I got it.
You're fired, right?
Exactly. It's got to be containing one UDP packet. Oh. Okay, thanks for listening.